Now, just to recap, what we've talked about, in the past we've talked about regular languages, context-free languages, context-sensitive languages, and recursively enumerable languages. And when we put these all together, we want to make like one big picture out of this. There's a famous professor at MIT named Noam Chomsky, and he's a natural language professor, not a computer science language professor. You know, natural languages like, you know, English and Italian and whatever. And he did a lot of study on this, and there's a big overlap between what we're studying in this course and natural languages. So just to do like kind of a high-speed review of what we've talked about. An example of a regular language is a language that can be accepted by a finite automata. So here's just kind of a random language. This is a language where you have to, your word has to start with an A, and then for as many times as you want, it could be followed by a BA, and then another BA, and another BA. So if we were to create a finite automata for it, we would have a start state. And if we read an A, we go to a state that we are calling a yes state, meaning if we end up in this state, we'll answer yes. And if we end up in any of these states, we'll answer no. So if the first thing we read is a B, that's no good, because it has to start with an A. So if we read a B, we go to, this is what we sometimes call a trap state. If you ever get into this state, and then any A's and B's you read after, you just stay here. You'll never answer yes. So if you ever get into this state, the answer will always be no. But if we read an A, we go to a state that says, oh, okay, this is an acceptable word. Now, if we read a B after it, we go to a state that says it's no good. But if we read a B followed by an A, then we're back to being good again, right? Because this is the language where we have an A, and then you can have an infinite series of B's followed by A's. So we can read an A, then we go B, A, B, A, B, A. Do this forever. If we do anything other than that, we're going to slide into this state and stay here. So this is a finite automata for that language. Now, every language has a corresponding grammar to it. And if you think about it, the grammar would basically be, we have a start, like maybe this is the S state. We start here, and then we have to see something that takes us to another state, and then we'll come up with a symbol for this state. So what we're going to do is we're going to have a grammar, we'll call this S, the start state, and then this state will be the X state. I'll just randomly pick a letter X, meaning I'm in that state, and then I'll describe if I'm in this state, what do I need to see to be an acceptable word, to eventually go out to a yes state. So the corresponding grammar for this language would look like this. We would start at basically a start state. If we see an A, we're kind of moving to another state. And then from that point, what do we need to see? Well, what we then need to see is a B and an A. Well, first of all, we could read an A and then see epsilon, which means nothing. That's the empty state. Or we could read a B and an A, and then we're right back in the same state we were in. So what I wanted to point out is that this grammar corresponds to this state machine. So this is basically, we're starting in state X, we require that we see an A, and then this is state S. We require that we see an A, and then we're calling this state X. And then as long as we see a B and an A and a B and an A, we can see as many of these as we want, or we can just stay here, meaning we've read nothing. That would be the epsilon. Those are considered acceptable words. If we see anything else, we're going to consider it a non-acceptable word and get rid of we're going to answer no. So this is kind of like the intuitive looking at the picture and writing the grammar. But we could consolidate it into a one-line grammar. We could say we start with a word, and it's either an A or something acceptable followed by a BA. And the only thing acceptable would ever be an A or a BA with an A with a BA, and then this could become an A with a BA again. So this is a grammar that so anytime we have a grammar where our big symbols, so the big symbols basically break down into little symbols, and eventually goes to these letters. And if all of the little letters are on either the left side or the right side, of a big letter, that grammar would then be considered regular. If there are symbols that have to be on one side of a big letter and other symbols on another side, that's going to be a higher level language. Okay. Now this is going to come up a little bit later. If you remember, we talked about recursively enumerable languages. There is the concept of we can have a language that we can enumerate. So if we wanted to print out all the words that are in this language, we could write an enumerating program. And what we basically do is we call the program with a string S, and we print out an A, and then we take S and we concatenate a BA on the end, and we call the program again. And it'll print out an ABA, and then add another BA onto the end, and call itself again. So here we would be recursively printing out, or recursively enumerating the entire language. And we can call it with an A to start with. So we call the enumerator and let it run. Now this would run forever, right? Because we just keep concatenating a BA onto the end of the last thing we printed and print that one out. So we are recursively enumerating this language. So we say that this language, even though this is a regular language, we can also say this is a recursively enumerable language. Meaning we can write a recursive program that can print out every word in the language. Okay, that's going to be important to understand a little later when we talk about higher levels of languages. Okay, just a couple of properties for now. Regular languages are a finite state automator can decide the language, meaning it will always, if you give an input word and you're asking yes or no, is this in the language, we can build a finite automator that doesn't use any memory and will always answer yes or no for all inputs. And there's also either a left or right linear grammar that exists for that language. So this is kind of the simplest form of languages. Okay, then if you remember, we moved to the next topic, which was context-free languages. So this was a language where, and probably the simplest and most popular example is the A to the I, B to the I. That means the number of A's and the number of B's have to equal each other. And the only way I think we talked about this when we talked about context-free languages, we said the only way we could build a state machine that can answer yes or no for all possible inputs is somehow we had to count up how many A's there are and then make sure the count of the B's matched. Now if we had one memory cell that was allowed to go as high as infinity, we could solve this, right? So what we would do is we would start in a state, we say if we read an A, we would add 1 to the counter, and then we'd have to read a corresponding B, and minus 1 from the counter, so if the counter hit 0. But a piece of memory that is actually, it takes a little, a little thinking, what would be the best word? Having less computing ability would be a stack, where you can, as we read symbols, we can push the symbols onto the stack, and we're only allowed to read or access the top of the stack. We're not allowed to read all the storage in it. The stack could actually be considered a state. We could actually even multiply the values on the stack and come up with a number that represents the content of the stack. So a stack is much less computing, has much less computing power than one memory cell that can go off to infinity. So if we have a language where we're going to bounce around from state to state, and we have the ability to push and pop off of a stack, we could write an automata that uses a stack to answer yes or no to all possible inputs of this language. So if we start in this state, and then every time we see an A, we push an A onto the stack. If we see another A, we push another A, we push another A. We keep doing that. And we're basically pushing A's onto the stack. And then when we have to finally see some B's, so if we read a B, we pop an A off the stack, and we go to this state that's, we're calling a yes state, but there's another condition. We could continue to read B's, and keep popping the stack. And if we read anything out of line, we go into this trap state where we'll always answer no. After we have read the entire input, if we are in the state of yes, and another condition, the stack must be empty, then we can officially answer yes. If we're in the yes state, but there's still stuff on the stack, what that basically means is we read more A's than B's, so we'll answer no. So we have a finite state machine that every time we read an input, we may read or access the stack, we may not, that's our choice. And we have to end up in a yes state, and we have to write conditions about the stack. So in this case, the stack would have to be empty for this to be a language that is, for this to answer yes or no to any word in that language. So this same language has a grammar that goes like this. We have a start value, an acceptable value, which would be an A and a B. Or any word that has been accepted before with an A in front of it and a B after. So for example, AB is good, and then A, AB, B is good, and then A, what we just had before, AA, BB, followed by B is good, and so on. So it's really one line is the grammar for this language. But what's being captured here, because every A must have a corresponding B, is going to require more than just a state machine. It's going to require some kind of memory. And the memory of a stack is plenty to solve this. And the stack, like I say, is it's a very limited piece of memory equipment. As we go on through this hierarchy, we're going to add more memory. Okay, so, and yeah, I'm just doing this to show that we could recursively enumerate this language. We start with, we call this the AB enumerator. We start with a blank, and the string S comes in, we put an A in front of it, concatenate a B after it, and we print it out. And then we call it again. And it puts an A in front of that input and a B after it and prints that out. And it'll print out, this program will print out AB, then AABB, AAA, BBB, and just go on forever. So we can recursively enumerate this language. Okay, properties of context-free languages is the languages are decided by a finite automata with a stack, which is also known as a push-down automata. And we can express, it can be expressed with a context-free language, context-free grammar. That's where the big symbols, like the big S, can be written as small symbols with a big symbol between them. But symbols can be on either side of them. They don't have to be left linear or right linear. Right. So, and that's basically keeping track of what the stack can handle. Okay, so now this is just like this is a very small version of the English language, just to capture the idea of what parsing a language is. So we have a start symbol. This is kind of like our big S. When we say a sentence is a subject followed by a predicate. Then we say, okay, what's the definition of a subject? So we're breaking down, we're basically taking, like as input, let's say we were to take an English sentence and ask ourselves yes or no, does this sentence belong in the English language? We'd say, okay, we start with a sentence. Well, the sentence has a first part and a second part, and then we describe the first part. And the first part is a bunch of adjectives, followed by a subject, and maybe another adjective. So this is like a left linear grammar. And then eventually it could be a noun. Then we have a predicate, which describes what the noun is doing. And we can have an adverb followed by a predicate, another adverb, and then we eventually have a verb. And then examples of adjectives could be like the, brown, big, etc. And adverbs could be loudly or quietly, etc. Nouns can be like a dog or a person. Verbs can be like barked or spoke. So this is not the grammar for the English language. It's a subset of the English language. There are other sentences that are allowed. But if we were to, and I just wanted to go over an example in English just so to show that we're doing something very similar. If we were to parse the big brown dog loudly barked, we'd say, is this a sentence? Well, maybe it is, maybe it isn't. Does it start with a subject and end with a predicate? Okay, that depends. Let's break down what a subject is. Well, a subject can be a the followed by a subject, because we said it could be an adjective followed by a brand new subject. And then followed by a predicate. So the big, so the subject, which was big brown at this point, became big followed by brown dog, and then it became big brown dog followed by a subject, and then the big brown dog followed by a noun, and then it was, so we now had this officially parsed into a subject. Now we're trying to see if what follows that is a predicate. And then the big brown dog, and then bark followed by a predicate, and then the big brown dog loudly followed by a verb, and then loudly. But I should have had, this actually should have been loudly.
Loudly, yeah.
Yeah, loudly, that should be good.
Loudly and then like loudly bark.
Right, and then eventually we say yes. So we ran it through a parser, and so it kind of looked like, we wrote this is a simple version of the English language, but this is actually a regular language, because we decided that all the adverbs and adjectives are on the left side of the nouns and verbs, which is not required in the real English language, so it's not, I'm just doing that kind of to make a point. Okay, so now we're going to move on to, we've talked about regular languages and context-free languages. Now let's look at a more interesting language. Let's take the language where the number of A's is equal to a power of 2. Okay, so for example, AA is in the language, 2 A's, 4 A's, AAAA, 8 A's, 16 A's, but all the other ones are not allowed. And let's say the whole alphabet for this language is just the letter A. Okay, so is this, can we create a finite automator, maybe with a stack that can print these out? Or do we need like more equipment? So first thing we ask ourselves is, can we even enumerate the language? Okay, so this will be the power, A to the power 2 language. Well, we can take a language and, oh, this should have been, oh no, right, okay. So we can take a letter like A, and then we say, okay, take A as input and concatenate an A next to it. So we have AA, we print it out, AA, and then we call the program again with AA as input. So now we take AA and AA, which is 4 A's, print that out, call it again with 4 A's. Now we have 4 A's and 4 A's, that's 8 A's, print it out. So we can enumerate this language. Nope. Almost all languages can be enumerated, recursively enumerated, printing out the results of that. But now the question is, how would we build this language? So let's look at it from a grammar point of view first, because sometimes the grammar sometimes gives us the insight to the equipment we need, which is like a state machine and maybe some memory. And sometimes the state machine gives us insight to what the grammar is. So this is a kind of a confusing grammar. I remember when I first saw this, I had to spend a lot of time with it. But here's what we're basically doing. What this grammar is saying is we're starting with an S, and then seeing if it can break down into smaller parts till we finally, can finally answer yes or no. So what's really happening is here, these big symbols A and B. A is a marker for the beginning of the word, B is a marker for the end of the word, and then inside the word we either have 2 A's, or 4 A's, or 8 A's, and so on. And these are the rules that check that we get there. So what we're going to do is, we're going to have this letter C go sliding through all the A's, and we start off with 1 A. We're going to let it hop over all the A's, and every time it sees an A, it's going to double it and turn it into 2 A's. So when we see a C followed by an A, we turn it into 2 A's and push the C after. So basically the C is going to go from starting at A and ending at B. Every time it sees an A, it turns it into 2 A's. Okay? So every CA turns into two A's with the C after it. So if we had 8 A's here with a C before it, it would scan over the 8 A's and turn them into 16 A's as it was hopping over them. And then when the C gets to the B, a C right before a B, we want to take the big letter C and slide it back to the A again, and then go and double them all again. So we can turn, anytime we see a C right before a B, that means we've gotten to the end of the word, turn it to a D, and then have the D hop over all the A's until it gets back to the A, and then go through the string again, doubling all the A's. So basically, if there was a, I kind of wish I had the marker right now, but if we had an A followed by if we had an A, a big A followed by a big C, followed by 8 A's, the C would hop over each A, turning them into 2 A's. So by the time it got to the end, we'd have 16 A's, and then we would change the CB to a DB. And all DB, a CB to a DB. And then the D would be after all 16 A's. And the D can just hop across all the A's, leaving them alone. So ADs become DAs, meaning we're just hopping the D over the A's back till we hit the beginning again. When we get to the beginning, we change the D to a C, and then it starts hopping across all the A's, doubling them again. And then eventually we want to say we're ready to stop. So eventually when the C marker gets to the B, we turn it into an E, and an A followed by an E becomes an E followed by an A, so the E marker goes back to the beginning till it lines up with the capital A, and that becomes an epsilon. So it's a little confusing how this grammar works, but the issue is this. This grammar will take any word that has a power of 2 of A's and answer yes or no. Now what's interesting about this grammar, and this is really where we get into the concept of, this is kind of an important concept, of whether a language is guaranteed to always answer yes or a no. In this language, these are symbols. All of these are symbols. A, C, little a, and big B. The big symbols can be broken up into other stuff. The big symbols get converted into other stuff. If every time, kind of like, so this is kind of an important concept. If we go back to this English language example, if a sentence breaks down into smaller parts, and then each of these smaller parts get broken down into, if each time we do a breakdown, if each time we apply one of those rules of the languages, if it breaks down into stuff that's bigger than the previous time, we're going to eventually get to these words, the words of the language, not symbols that mean a couple of those words. We'll eventually get down to individual words, and we'll stop. But if any of these rules say, like a predicate and a subject could turn into one thing, then we're not always getting wider and getting to an answer yes. We could have, so for example, we could have this one symbol turns into 4 symbols, but these 2 symbols become 1 symbol. So what we're parsing could get bigger and smaller and bigger and smaller and bigger and smaller, and we may go on forever. We're not going to get bigger and bigger and bigger until we match the input word. We could get into an infinite loop where we're getting bigger and smaller and bigger and smaller. So if we made a rule that said all productions, all of these rules, these are called productions, have to have a property that we never have, and I put the 2, I highlighted the 2 that don't follow this property. If we said that all productions, the number of symbols have to equal, the number of symbols on the right side have to be at least as many as those on the left side, then we can never make the word get smaller, then bigger, then smaller, then bigger, and possibly go into an infinite loop. So if we say we can write a grammar for a language, and we say that a language that has these 2 problem productions, we call this an unrestricted grammar. And what this basically means is that it is possible, if we allow productions like this, it's possible for us to start parsing a word and never actually get to the point where we have just letters in the language. We could get stuck in an infinite loop of productions. So Okay, so now, we'll get back to that kind of language in a second. Now I just want to talk about the complements of languages. Okay, so this is now, once again, we're back on the topic of enumerating a language. Suppose we wanted to have the language, all the words that are any combination of our alphabet. So our alphabet is A's and B's, and we want to print out every possible combination of, so we're printing out the universal set. So what we're doing is we're saying, print out every combination of A's and B's. So we write an enumerator that takes as input nothing, blank, concatenates an A onto the end of it, prints it out, concatenates a B onto the end of it, prints it out, and then recursively calls itself with the A word, oh, this should be a B, sorry about that, that should be the B word. So that's the B word, and that'll recursively print out, it'll print out an A, and then a B, and then two A, an AB, a BA, and a BB, and then all of these words with an A on the end of them, and all of these words with a B on the end of them, which would be all of these, and it'll just go on and on forever. And it'll eventually print out the entire, every combination of every word that could be made with the letters of A and B. Now suppose we wanted to print the complement of a language. So suppose we had all the words such that they are not words where it's a bunch of A's followed by a bunch of B's and the numbers match. Suppose we want all the words that are, in other words, we want all the words not in this language, right? That's the complement, remember, from set theory. So that would be kind of like printing out the universal set, but don't print out the ones where, only print out the ones that are not members of this language. So we would, be the same code as before. Again, this should be SP. But now, as we generate them, we say if it's not in the AIBI language, which we built a finite automata with a stack earlier where we can check yes or no if it is. So we're just calling that routine, and then we print it. So we're basically enumerating every word we can make out of A's and B's, but we're skipping the ones that meet the condition that the number of A's and the number of B's equal each other. So it's the same output as last time, except the AA and the BB are missing. These are all fine because they're an odd number of letters. So we can enumerate a language, and we can enumerate the complement of a language. Okay. So that was just a side thing I wanted to throw in, because this is going to all kind of come together. If in all of our productions, if we say that what's on this side, so this is maybe a bunch of symbols here, becomes a bunch of symbols here. If we make a rule that says the beta side is as big or bigger than this side, then we will be guaranteed, as we're taking a word as input and parsing it, will eventually get bigger and bigger and bigger, and the size of all our symbols will equal the input word, and we can stop. Or if we produced a word bigger than our input symbols, then we know we'll never shrink down and match the input symbol, so we can answer no. So if you follow this rule for grammar, that the right side has as many symbols or more than the left side, then we will always be guaranteed to let the program run and eventually answer yes or no for all inputs. It'll answer yes or no. We'll never go into an infinite loop. Okay, so a recursive language is the new definition. It's a language where we can build a finite automata machine with some memory. So now this is, when I say some memory, we'll have another class where we talk about a Turing machine. But right now we're saying some kind of memory, maybe a stack, maybe even more memory than that. But if we can build a finite automata with some memory, and for all possible inputs, we could always answer yes or no. We'll never go into an infinite loop. We're going to call that a recursive language. And then all languages that have a restricted grammar, meaning the beta side is as big or as big as the alpha side, those are restricted languages, and we're going to call those this new name context-sensitive languages. So those context-sensitive languages are languages that will always produce a yes or no. Okay, now languages that are recursively enumerable. So I've showed throughout these slides, I've showed many languages and how to recursively enumerate them. So if we have a language and we say, is this thing recursively enumerable, all you have to do is be able to write a program that could just recursively spit out every member of it. That doesn't mean you could recursively enumerate the complement of them, but if you can print out, if you can write a program that can enumerate all of the members of the language, which would be all the things we would answer a yes to, then that's a recursive language. If you try to enumerate everything that was an answer of no, it may go into an infinite loop. It's still recursive. As long as we can answer yes for members, as long as we can answer yes for members or recursively enumerate the entire language, it's considered a recursively enumerable language. An example of a language that is recursively enumerable, but its complement is not recursively enumerable, is the famous halting problem, which was presented by Torp. Okay, so, I'm sorry?
Halting problem, we have seen it yesterday, last class, halting problem.
Right. So for example, now what if a language is, suppose we could build some piece of equipment that could recursively enumerate a language. In other words, print out every member of the language. And then suppose we could recursively enumerate its complement. We could print out everything that's not in the language. Like just before, we wrote a program that will print out every string that is not a number of A's followed by a number of B's where the numbers match. Every string that doesn't meet that condition. So suppose we could write a program that can print out every member of a language, and then a separate program that prints out every member that, this is a L complement. I couldn't get, in Visio I couldn't get a bar across the top, so this means the complement of L. So if we could recursively enumerate the complement, meaning print out every member that's not in the language, then could we build a machine that always answers yes or no for that language? And we could by doing a time sharing thing. Some authors call this a dovetailing thing. Let's say we wanted to know is the word A, B, A, A in the language where the number of A's and the number of B's equal each other. This program, which is spitting out every word in the language, so this program spits out A, B, A, B, B, A, B, B, B. This is printing out all of those. This language prints out everything that's not in this language. So this is going to print out A, B, A, B, BA, B, not BB. You know, all the words that are not in this language. Eventually, one of these two machines that's either printing out all the words in the language or printing out all the words that's not in the language, eventually one of them is going to print this thing out, right? So if we wrote this to say, instead of printing them out, compare them to this, and if they match, answer yes. So if this thing can recursively generate all the members of the language, and this thing can recursively generate all the members not in the language, eventually one of these two machines is going to match this. And if this one finds a word that matches this, then have this thing answer no. So this is kind of the overall design. This is the overall design of a machine. And also now the other thing, this time sharing part. What we're going to do is we're going to write some code that says, okay, let this one run for a little while, like 5 minutes, 10 minutes. Then let this one run for 5 minutes, let's say 10 minutes. Then let this run for 10 minutes. Then let this run for 10 minutes. And do that forever. Eventually, one of these is going to go, I found it. And if this one finds it, it's going to spit out a yes. And if this one finds it, it's going to spit out a no. But any word we put in this machine, we will always be able to answer yes or no. If neither one of these goes into an infinite loop, we'll always be able to answer yes or no. So what we're saying here is if a language and its complement can be recursively enumerated, if you can print out every member of the language and every member of the complement, then that language, there's a special word, means it's recursive. We could write a recursive function that could always answer yes or no if the word is in the language. And the other thing we could do, we could recursively, like that example where I had the universal recursively enumerated the universal language. We could do that and then just ask ourselves, are we here or are we here? So we could, that would make this language recursive, if we can answer yes or no to an input. So this is the overall, the picture, I wanted to make, comes out different when it's coming out of the projector. I wanted to make, so all languages that are regular are languages that can be answered yes or no with a finite automata. And if you put an input word and we run our test, we will always answer yes or no. Context, so I wanted these three to be green and this one to be red. And I wanted them to have different shades of green. So these two kind of came out the same, so sorry about that. So the words that are context-free are languages that if you give an input word, we get to create a state machine plus make use of a stack. And we can always answer yes or no if it's a member of the language. Context-sensitive were words. Now this is where we said, as long as all the productions in the grammar never shrink. So what we basically said is all productions, anything that's on the right side has to be as big or bigger than what was on the left side. So as we're building words in the language or testing words, we never get smaller. And we will eventually grow big enough to match the size of the input and we'll either answer yes or no. If we ever grow bigger than it, if we're generating words following the rules of the language and we grow bigger than the input word, we will never shrink back down and match the input word. If we grow past it, we're done. The answer is no. So for context-sensitive languages, we can always answer yes or no. And they have that rule that the productions, what's on the beta side or the right side, has to be as big or bigger than what's on the left side. And what that translates into is the equipment we're going to use for context-sensitive languages is a state machine and a chunk of memory that is linear in size to the input word, and we'll never be in a situation where it grows bigger than a linear bound on the input word and shrink its way back down to the input word. So in this case, in the context-free case, we're using a stack. In this case, we're using kind of like a stack, but we get to look at all the contents of the stack. So it's really like a linear piece of memory that is linear in size to the input. So in all three of these cases, we will always be able to answer yes or no for any possible input you can give. So what that means is, in all three of these cases, we can recursively enumerate the language, and we can recursively enumerate the complement of the language. For any language that's in this, what should be the green circle. And then the question was, like almost intuitively, you'd think the whole world is in this, in this context-sensitive circle, because you'd ask yourself, is it possible that we could dream up a language that says, we built up some machine, a state machine and some memory, and then we start processing a word, and we're trying to answer yes or no, is it in the language? And as we're processing it, now if we go outside of this, where we don't have that restriction that all productions have to generate bigger productions, if we can make bigger productions and then bigger productions make smaller productions and go so on back and forth, is it possible that we could dream up a question where instead of answering yes or no, for some inputs we can actually end up looping forever? And that's the one Turing came up with, the question, the halting problem is an example where, and again, review the lecture on recursively enumerable languages. But the idea was, if you had a program and you gave it an input, would that program go into an infinite loop or would it stop? And the answer to that question is, so you're taking as input the program and its input, and you're asking, will it stop or will it halt? Because the thing is holding problem. Will it halt or will it go into an infinite loop? And Turing proved nobody could ever write a program that would answer yes and no for all possible inputs. You could argue that you could answer yes on the yes side. You could enumerate them by taking every possible program and every possible input. And if it halts, spit out yes for all those. But the ones that don't halt will just loop forever. So that was one example, and then from that example you can make a lot of copycat examples after that. So these 4 layers, I was kind of hoping this was 3 different shades of green. Green meaning go and red meaning stop, I don't know. But that from context sensitive on down, if you can build a language as a context sensitive or using less and less memory, it gets smaller and smaller, we always answer yes or no. But once we get into the languages that are recursively enumerable, but the complement of the language is not recursively enumerable, those are languages where we can always answer yes if the input is a yes, but if the input is a no, we may go into an infinite loop.